We'll move on to the fourth of 6 talks of this session from Lukas Furtak, the very low mass end of the redshift 6 to 7 galaxy stellar mass function challenges and SED-Fitting. So Lukas, feel free to unmute yourself and go ahead and start when you're ready.
Okay, hi everyone. Thanks, Steve. So yes, I'll be talking about how we constrain the very low mass end of the stellar mass function at redshift 6 to 7. So my name is Lukas. I'm a PhD student at the Institute for Astrophysics in Paris, and I've done this work with my advisors Kim Tech and Matt Leonard. So yeah, let me give you a quick rundown of stellar mass function at redshift 6 to 7. So mass functions at these redshifts have been measured up to now down to 10 to the 7.5 solar masses in blank fields, and down to 10 to the 6 solar masses using strong lensing clusters. So the general trend observed is the steepening, is a notable steepening of the low mass end slope with increasing redshift. However, measuring stellar mass functions and stellar masses is model dependent, unlike terrestrial UV stellar mass functions, because the stellar mass that we get from photometry will depend on other physical parameters such as stellar age and dust attenuation, etc. So this work is an attempt to test how these other parameters and assumptions we make on these other parameters are going to impact the shape of the low mass end of the stellar mass function. So for that, we look at the 6 Hubble Frontier Fields clusters, which are very well studied strong lensing fields with very deep HST photometry. And when I say I look at very faint, very low mass objects, I mean beyond 26 magnitudes. So we really need the strong lensing effect to even detect these objects. And lensing enables us to detect objects down to -12 absolute UV magnitudes. However, that being said, the systematic uncertainties that come from strong lensing modeling actually induce very large error bars in these objects, meaning that let's say we can robustly constrain the faint end of the luminosity function down to -15 UV magnitudes. So I worked with a sample of 300 redshift 6 to 7 galaxies detected in the Hubble Frontier Fields. And as Victoria has already said in the talk before, what really is crucial to constrain physical parameters at these redshifts is the rest frame optical photometry, meaning Spitzer photometry. So luckily, the Hubble Frontier Fields have been observed to very deep depths in the Spitzer with the Spitzer telescope. So we have this rest frame optical photometry to constrain stellar masses. So how do we measure stellar masses? Well, that's done through SED-Fitting with a code called the Beagle tool. And so in order to test how these different physical parameters are going to impact the stellar mass function, we first construct a kind of a minimum parameter and assumption model. So SED-Fitting configuration where we fix as many parameters as possible and make the simplest assumptions possible. So in this case, we fix the metallicity at 0.1 solar metallicities, assume a constant star formation history, and limit dust attenuation to very low levels. Because since most of these objects have very blue UV slopes, we expect them to have extremely low dust attenuations. And then departing from that model, we're going to just change single parameters and run more SED fits in order to test how these are going to impact the mass. So when computing, so we then use the whole bunch of SED fits that we've done on these galaxies to derive empirical mass to light ratios and convert the faint and UV luminosity functions to stellar mass functions. So since our sample mostly probes galaxies below 10 to the 8.5 solar masses, we combine these stellar mass functions with some high mass end points observed in blank fields in order to constrain the whole shape, the total shape of the stellar mass function, and then fit these stellar mass functions with first with the classical Schechter function, which you can see on the left-hand side plot, However, as you can see, the mass function departs from the classical Schechter form at masses lower than 10 to the 7 solar masses. So we also fit them with another modified Schechter function that is going to allow for a downward or for a turnover below 10 to the 7 solar masses. However, if you have a close look at the error bars at the very, very low mass end, they become quite large, if not to say very large. Which in this case is mostly due to strong lensing systematics. So at this point, the error bars will also be consistent with the mass function not turning over or even steepening at the very low mass end. So this turnover is not very well constrained. So how do these SED-Fitting assumptions now impact the stellar mass function? So for reasons of time, I'll just talk here about the most extreme cases I find. So in this plot up here on the left side, you can see the solid blue line. That's the minimum assumption model that I've shown earlier. And then the most shallow case of stellar mass function that I find is the dashed line, which we get for assuming exponentially rising star formation histories. And the Nash dotted line is the steepest star formation, the steepest stellar mass function I find, which we get for allowing large ranges of dust attenuation within the observed galaxies. So in total, all these SED-Fitting models we apply span low mass end slopes from -2.2 to -1.7, so quite a large gap that we get just from changing single prescriptions in the SED-Fitting procedure. So why this is important, you can see why this is important on the plot on the right side down here, especially in this panel, where you can see that the low mass end slope and the high mass end cutoff are strongly correlated in stellar mass functions. So that it means we need to constrain both the low and the high mass end of the stellar mass function in order to constrain the whole shape of the stellar mass function. So in explaining where these differences come from, so I've tracked down what happens when we apply exponentially rising star formation histories and what happens when we apply higher dust attenuation levels, and basically both can be tracked down to either a lack of rest optical photometry, Spitzer photometry, or simply that the optical nebula emission lines such as O3 lines and H beta are redshifted into the Spitzer IRAC bands at these redshifts. So let me first talk about Spitzer photometry. So since Spitzer has a much lower resolution and much worse point spread function than the Hubble Space Telescope, since we're looking at galaxy clusters, which are naturally crowded fields, there are a lot of galaxies, foreground galaxies in it, we get a lot of contamination by either intercluster light or from the cluster galaxies themselves in the photometry of these very faint high redshift objects, especially if there's a bright galaxy nearby. So in the lower frame, you can see a typical redshift 7 galaxy in a Hubble Space Telescope frame versus what the same galaxy looks like in Spitzer. So it becomes very hard to get accurate photometry in these Spitzer frames. So after selecting sources that are that have really absolutely clean and trusted IRAC photometry, this is actually a pretty small sample of our galaxies, and these are mostly bright galaxies. So on the high mass end, so the very faint, very low mass end galaxies, most of them don't have any IRAC photometry in our sample, which means that these very faint and low mass galaxies are going to be mostly constrained by rest-term UV photometry only, which is not really suited to measure stellar masses, right? And these very low mass galaxies are therefore most heavily affected by allowing a wider range of dust attenuation, since dust attenuation is going to affect the UV wavelengths much more than it does the rest-term optical wavelengths, which leads to a slight shallowing in the mass to light ratios for these galaxies when we allow for larger dust attenuation, which then with a shallower mass to light ratio, we get the steeper stellar mass function in the end. So this is why this explains the steepest stellar mass function that we find. So something like this will typically be somewhat alleviated when we observe distant galaxies with JWST, because the near-cam imager is going to be able to get this terrestrial optical photometry at the same resolution and depth as the Hubble Space Telescope photometry. So we can there we will be able to constrain the photometry of these very faint galaxies. And there's also been a couple of papers out recently that simulate how some MIRI photometry is going to alleviate this dust attenuation degeneracy. So the second problem, which results in the most shallow stellar mass functions, are these nebular emission lines, which contaminate the terrestrial optical photometry. So when applying when assuming an exponentially rising star formation history, we get lower stellar masses by 0.4 dex, so quite a lot lower, which is basically down to a rising star formation history means larger star formation rates, which mean the emission line equivalent widths in the Spitzer IRAC bands are going to be much larger and account for a much larger fraction in the flux, meaning that the same galaxy is going to be fitted with much lower mass. So the overall lower stellar mass distribution is going to result in a shallower stellar mass function. So for this, we're going to eventually require a near-spec spectroscopy of these terrestrial optical emission lines to disentangle the emission lines from the stellar continuum in order to constrain stellar mass. Another parameter that is heavily affected by this is the stellar age. So usually when when SED-fitting high-redshift galaxies, one just leaves the stellar age and the stellar mass as free parameters. However, we find that by doing this, we basically allow for a too large a range of equivalent widths. So when just changing the lower boundary of stellar age in this kind of fit from 10 million years to 20 million years, or the other way around, from 20 million years to 10 million years, we get a difference in resulting stellar mass distribution of 0.5 dex when just changing the lower boundary of age. As you can see in this plot over here, you see the best fitting SED for a galaxy, and in red you see the best fit with lower boundary of 10 million years, and in green lower boundary of 20 million years. So you need to be while nebular emission is very important to correctly model these as the SEDs of these sources, so nebular emission needs to be included. However, need also to be careful what then happens, because including nebular emission means that we cannot, at least at redshift 6 and 7, where most of the optical emission lines are redshifts into both the IRAC frames, we cannot really disentangle the nebular emission from the stellar continuum. So as I said, this will new constraints on this will come with the JWST near-spec spectrograph, which will be able to measure these equivalent widths at these redshifts. However, this will mostly be able to measure them for the bright, so the high mass end galaxies, meaning that on the very low mass and very faint, very low mass end, we will still be dealing with some of these issues, even in the JWST era. So let me leave you here with my summary slide. So while we do observe stellar mass functions down 10 to the 6 solar masses, we do also find them to be heavily affected by SED-fitting assumptions and prescriptions on the parameters. So they span a range from -2.2 to -1.7 on the low mass end slope, mostly due to either the lack of accurate terrestrial optical photometry or due to contamination by the nebular emission lines. A third point I've not been speaking about here because of time is that we also get very large strong lensing systematics, which induce very large uncertainties on high magnification factors, i.e. on the very low mass, faint low mass and galaxies. Right, that's be from me, and thank you for listening.
All right, thank you, Lucas. So I think we have time just for one question. And so, well, with the most votes, where did it go? From Nathan Adams, who asks, how have you handled sample completeness in the low mass regime?
Sample completeness in this case was computed for the UV luminosity functions. It was computed by modeling, basically by injecting sources in the source plane and then running them all the way through the lensing model to see how they arrive in the image plane.
All right. Well, thank you very much, Lucas.